Thank you very much for your kind introduction. Okay. Kind introduction, Professor Cho. My name is Kiyono from Kyoto University. It is my great pleasure to have the keynote speech in 8th Asian Conference on Earthquake Engineering and here in Enquiry. So my topic is related to the lifeline system. So at first, I introduce the lifeline system because my topic is very specified. So at first, I introduce the lifeline system, and after that, I talk about my main topic. So introduction of lifeline system. So this is evolving concept of critical infrastructures. The critical infrastructure is similar in all nations due to the basic requirement of life. So I introduce at first about the critical infrastructures. And in 1980s, so emphasis on public sector. This is defined by US. And at that time, the US classified the critical infrastructures in 16 sectors. But as you know, the critical infrastructures deemed critical can vary according to a nation's needs or resources or development level. But this is defined in US in the public sector. So transportation, government service, or telecommunication system, and water. So my topic related to the water supply system. And this also extended to another sectors after 9/11 in US. Chemical industry, agriculture, food, and so on. So this is the lifeline system defined by Duke in 1975. He classified the four: the water supply and the treatment system, and that is the water and the sewage system, energy supply system, electric power, gas, and petroleum, and transportation system, road, railway, harbor, aviation, and telecommunication system, telephone, internet, radio, TV, newspaper, and mass media. And also, we classify the lifeline in two types. The one is the one-way source transmission and the distribution, from source to distribution. That is, today's target is the water supply system or wastewater for energy, electricity, and broadcast communication. That is one way. So another type is network, many sources and many destinations. That is transportation system or telecommunication system. Today, I talk about the water supply system. And this is a one-way system. Source, many type of sources. The lake, or artificial, like a dam, natural lake, and a river, and a well. So we intake the water from this source and convey to the purification station, that is the treatment station, that is a conveyance by aqueduct, canal, pipe, and a tunnel. We convey the water, raw water, to the purification station and purify here and transmit to the storage. Transmission method is gravity and pump up. And this is the storage. Storage is reservoir or tank. And after that, distribute the water to the consumer by pipe. There are many types of pipe: iron, cast iron, or ductile iron, or steel, or concrete, and polyethylene. So today's my presentation is about polyethylene pipe and this storage and pump station. Again, this is a schematic diagram of general flow of water supply system. A dam, lake, a source, or intake the water from the ground and convey and purify treatment station and transmit to the reservoir or reserve the water and distribute to the consumer. So this is the general flow of the water supply system. So my topic is about this distribution pipe. So this is the research topics on lifelines and seismic excitation. So when we consider the behavior of the pipeline or pipeline network or water supply facilities, at first we have to consider the fault and ground motion estimation. So we have to consider the fault mechanism and how is the wave generated and so on, and decide for the design ground motion. And seismic behavior of pipeline is very, very critical issues and very important. The deflection and the strain of the pipe and ground response and dislocation as well. If the fault running, we have to consider the surface fault dislocation or large ground deformation caused by liquefaction and ground failure. And the pipeline is usually buried underground. So the dynamic interaction between soil and the pipe should be considered. And this is the wide network. When we consider this kind of network, the seismic reliability of lifeline is indispensable. Prediction of the damage and restoration during and after the earthquake. And also we have to consider the socio-economic effect on urban activities. So the lifeline engineering play field is very, very wide. Okay, I talk about the damage to pipeline by past earthquake. Of course, in Taiwan, so very, very severe damage in 1999 earthquake, and China earthquake, two big earthquakes occurred in 2006 and 2018, 2016 and 18. And recently, in the far end, a big earthquake occurred. So in Japan, also severe damage to pipeline occurred many times. This is a typical damage photo. This photo is taken 2004 at the prefecture earthquake. Damage to water pipeline. In this earthquake, the main cause of damage is ground deformation or landslide, large deformation or landslide and liquefaction. So this is damage to water pipeline, water distribution line. And this is also the damage to pipeline, but not the water pipe, but the gas pipe. So medium pressure gas pipeline is damaged by ground deformation. You can find the gas pipe was buckled inside of the soil. Here and this. So this is the damage to the distribution pipe attached to the road bridge, and the damage caused by tsunami. Tsunami ran up and attack to the bridge and attach the pipe. In 2011, Tohoku earthquake. And 2018, in Osaka, the medium class earthquake occurred. But damage occurred to the water transmission line here. So this is underground pipe and breakage, and the water go up the road. And this is damage to the transmission line attached to the bridge. And some valve was damaged by maybe the shock wave and water flow outside. So this is the main topic of my talk: background, problem statement, and objective. So this is the background. So various loads stationarily imposed on ground pipeline, such as internal pressure, thermal change, temperature change, vehicle weight, and unequal settlement of the ground. The strain of the pipe is generated by these stationary load. And of course, we have to consider the behavior during an earthquake. So when the earthquake occurs, in addition to this stationary load, the ground motion causes strain to the pipeline. If the total strain by the stationary load, the dynamic load, exceeds a allowable level, the seismic safety of the pipeline is not ensured. Therefore, accurate evaluation on the strain of the pipe feasible for the assessment of the seismic resistant capacity and durability. So there are many pipe types. This is the steel pipe, the welded and the spiral welded steel, or flange pipe steel. And the upper right is the cast iron or ductile iron pipe. And the bottom left is concrete pipe. Many many types of pipe exist. And this is the polyethylene pipe. The history of the polyethylene pipe relatively new compared with this metal pipe. But the total length is increased more and more, and high seismic capacity and flexible. Compared with the metal pipe, very, very flexible and lightweight and low cost. So, this is a schematic diagram type of behavior, difference between the metal pipe and polyethylene pipe. Left figure shows metal pipe. So metal pipe buried in the soil, earthquake occurred, and the metal pipe, as you easily imagine, very, very large stiffness. So the elongation, so sliding easily occurred between soil and pipe because the pipe is very, very rigid. So the elongation of the pipe is very, very small. And the relative displacement due to the sliding is very large. So the effect of surrounding soil is very, very small. But today's target polyethylene pipe, the schematic diagram is this. Earthquake occurred, and this is the polyethylene pipe, but the stiffness is very, very small. So stiffness is very small, so behave with ground. So the elongation of pipe is very large, but the sliding is small, so the relative displacement is very small. So the effect from surrounding soil is very large. So it's very, very flexible pipe. So this is the model equations proposed by Japan Water Work Association, JWWA. Seismic Design Guideline, or JWWA, for water distribution pipe indicates the equations to calculate the strain by stationary load. The strain by these loads are added to earthquake-induced strain and evaluated, I explained before. And number one, number two, the actual strain by internal water pressure is this. And actual strain by thermal change is this. So another two is actual strain by vehicle load, like this. And actual strain by an equal settlement. There is an embankment, soil embankment on the surface ground, and that is an equal settlement would occur. But this 3 and 4 is due to the bending to the pipeline. And also they consider the effect of the soil because the calculation was done by the calculation of the beam on the elastic bed. So they consider the soil effect. But today, I focus on these two actual strains induced by internal water pressure and thermal change. So the problem statement and objective. So as I explained, the model equations 1 and the two are not taking into account the effect of surrounding soil. Just a calculation, only the pipe. The relatively the small stiffness pipe, such as polyethylene, is strongly affected by the condition without soil, because the soil constrains the movement of the pipe. So the current situation, they don't consider the soil effect. Therefore, here we propose the accurate equations taking into account the effect of surrounding soil by introducing the soil spring. The model proposed are verified by comparing with the past experiment and show the difference of the strain calculated without the soil spring. This diagram shows the internal pressure from the inside, and this is very equation, the elongation by the temperature change. The methods and the results. So this is the proposed pipe model taking into account soil spring. This is pipe touched soil spring. Very simple model. So introducing the soil spring and make the equation. So this is a small portion from the equilibrium of an infinitesimal element. And we make the equation by considering this equilibrium. And this is, U is the total elongation. UA is due to the axial stress, equilibrium of this stress, and UV is elongation due to the internal pressure or thermal temperature change. The first, I explained about the axial strain by internal water pressure. This is a section of half section of the pipe. So internal pressure act. It's difficult to put. Circumferential stress. This generated. And taking into account the Poisson ratio, so we convert to the longitudinal direction. The elongation by this internal pressure is this. Theta C is circumferential stress. And from the equilibrium I explained of the infinitesimal element, we get this equation. And introducing the k square and alpha. So finally, we get this kind of inhomogeneous differential equation. And we solve UA under the given boundary condition and plus UV. So finally, get this elongation and strain, axial strain, longitudinal axial strain. This is in case of the temperature change. The procedure is the same. Total displacement, U, is expressed by the sum of elongation due to the axial stress, UA, and elongation by temperature change, UB. And we make the differential equation and the same procedure, and given the give the boundary condition, and we get, finally we get this displacement and strain. So we compare this theoretical result with the experiment. The experiment outline is like this. The thermal change is about 25 degrees, and outside of the ground, and internal pressure change from 0 to 1 megapascal under the same varied condition. And overburden is 1.2 meters. That is the decomposed granite, the backfilling soil. And the length, pipe length is 20 meters, and the varied part of the soil is 15 meters. And in each 1 meters, they put strain gauge. So this is a diagram of temperature change, experimental setup. Total length is 20 meters. This is outside ground. The length is 20 meters. And inside of the soil is 15 meters. Hot and cold water flow that cause the 25 degree change of temperature. This is the water pressure. In case of water pressure, the setup is same, 50 meters and 50 meters inside of the soil, 1 meter, they put meters. So this is a result and the comparison experiment, theoretical one. The left is the result of experiment. This is free ground and inside of the soil and the 20 meters. Of course, the boundary strain becomes large. Maximum strain occurred in the experiment, and that value is 0.015%. Right-hand side is values from proposed equation. Change the internal pressure, same as, but 1 megapascal, because pipe is affected by the boundary condition. So we select the almost stable part, and the maximum the strain at 5 meters is 0.038, which is 1/4 value of the experiment. Next is a comparison case of the thermal change. So this is a result of experiment, and maximum strain is 0.001. And proposed equation, from the proposed equation, and the value is 0.005. So this value is 5 times larger than experiment. Someone thinks, so this difference is very large, and someone thinks this difference is very, very small. But we can find, if we compare the model equation, at first I explained this, proposed by J. They don't consider the effect of soil, surrounding soil. The calculation value is 0.229 in case of internal pressure. In case of thermal change, the actual strain is 0.3%. So the bottom is comparison of strain by proposed equation, experiment, and model equation. So again, the strain by internal pressure change, internal pressure, the proposed equation is 0.04, and experiment is 0.01, but the current model equation is 0.29. In the thermal change, 0.05, 0.01, 0.3. So this is several tens times larger, and this several 100 times larger. So this is a conclusion. So in this research, we consider internal pressure and temperature change, which are stationary load that might cause the significant deformation of pipe axial direction, and proposed the formulation by taking into account the effect of surrounding soil. We compared the result with experiment to verify suitability and usefulness. We found that the JWA model equation, which does not take into account the constraint imposed by the surrounding soil, yield excessively large strain. It is expected that effect of surrounding soil should be taken into account for the calculation of strain by the stationary load in seismic design of relatively low rigidity pipe, like such as high performance polyethylene pipe. Okay, thank you very much for your kind attention.